Okay.
Well, please, it's yours.
Can we begin?
Yeah, please go ahead.
Okay.
Okay. We are presenting on profiling the DRAM's raw hammer susceptibility from the operating system. In this presentation, we will discuss about the DRAM-based main memory. We will talk about its organization, working, and finally, one of the infamous problems associated with it, that is the raw hammer problem. The DRAM-based memory is most common choice for main memories. It's cheap and scalable. DRAM manufacturers have kept the cost low by trading off the performance. However, there are other concerning issues with a typical DRAM device. During manufacturing process, there exists some variation across the DRAM device. These variations are called process variation. It causes deviation of key parameters of the device from its nominal counterparts. A concerning study was done back in 2013 by Kim and others. They observed that on a DDR3 DRAM device, the last generation of DRAM devices, if the same cell is activated again and again, it causes an electromagnetic interference in the neighborhood. This causes faster draining of charged capacitors. This in turn causes a flip in the value of the capacitor. In other words, one can change the value of a DRAM cell without accessing that cell. This is a serious issue pertaining to DDR3 and its subsequent DRAM generations. It is predicted that this will get worse due to scaling. The mitigation technique is to charge the capacitor before losing its charge, then the sensing threshold. This is done by simply reading the entire row or rows in the neighborhood. DRAM manufacturers have installed a mechanism to prevent such bit flips. They call it target row refresh, or simply TRR. TRR is a closed implementation. It is differently implemented by different manufacturers, but the end goal is the same. However, recent research works have shown that there are ways to bypass the TRR by fooling the mechanism with complex access patterns. Therefore, we can't rely on hardware-based mitigation techniques only. We need an OS hardware combined approach which can communicate and thwart raw hammer attacks more effectively. All the while, we also have to ensure a low cost of implementation and performance overhead of such a technique. In addition, we also need to
just hold on for a second. I think your team at the earlier of this quarter already mentioned to me that why the DRAM manufacturer, when they talk about this, it won't work. Can you explain to me why it won't work? Why the hardware mechanism won't work? I forgot.
Yeah.
I just forgot.
Yeah, I can fill you up on that. So you see, there are around 32,768 rows in a DRAM. So before going to the definition, I just want you to look at how the DRAM looks like. So you can imagine the DRAM device is a two-dimensional array, and it is split across ranks, and ranks are further divided into banks. So each bank is essentially a two-dimensional array with rows and columns. Each row is susceptible to row hammer bit flips. So you have to count excesses of each and every row present on the DRAM device to accurately detect where an aggressor or where repeated activations or repeated excesses are being happening, which is an infeasible task because each bank has 32,768 to 65,536 rows. Even if we assume that we use 15-bit counters or say 16-bit counters for each row, the area overhead is extremely enormous. So instead of that, the DRAM manufacturers have implemented something called a target row refresh. So they don't have counters for every single access to maintain, but what they do is they sample those accesses. Say just assume that there are 100 accesses possible in a DRAM device. So they will start sampling. From 1 to 10, they will count all the excesses, whatever is happening in the system. From 10 to say 70, they will still maintain this count, but after 70, 71 onwards, they sample it. So they will just monitor, say 77. Is there an activation where we have the time at 77? No? Okay. If yes, just make a count of it. Then they will skip a few numbers ahead, say 77, 81, 86, 90, 95, 100 before everything is reset. So that is the reason, like they have limited hardware, and that is the reason why people are still able to bypass this mechanism, this mitigation mechanism.
Okay, so basically they're doing sampling about the assets.
Yes.
And then
yes.
Depending on how they do sample, that sometimes may be accurate. No, I'm just wondering that any mechanism has a shortcoming. I just want to see that because they just do sampling, so it has some probability that
Yes.
it might still get penetrate. Okay, that's fine. Thank you.
Yeah. So maybe we can skip this slide and continue on the row hammer problem.
Okay. Frequently accessing a particular DRAM row causes its adjacent rows bits to flip. This problem is known as the DRAM row hammer problem. It causes due to the electromagnetic interference between the DRAM cells, which is the result of large-scale integration in state-of-the-art semiconductor design. These bit flips cannot be corrected by the DRAM error correcting codes, which makes it a critical problem. It's a hardware fault. The row that is repeatedly activated is called an aggressor row. It's represented by blue in figure 2. In the same figure, the red blocks represent a bit flip in a column. These rows with potential bit flips are called victim rows. In figure 2, we demonstrate a row hammer attack. We are activating two rows repeatedly, represented by the actions 1 and 2. This causes bit flips in the neighboring rows. The victim row sandwiched between two aggressors has a higher probability of showing a bit flip. This has been shown by several research documents, especially for DDR4 DRAM devices. This is called a double-sided row hammer attack. TTR aims to find such aggressor excesses patterns. It samples excesses to determine it. At the end, TTR estimates frequent activations and not deterministically determines them. Therefore, a few research articles were able to bypass the TTR mechanism.
So as we have mentioned,
May I ask a question on the previous slide?
Oh, yeah, sure.
Yeah, just a quick. So I'm assuming that the aggressor cannot precisely flip a particular bit.
No.
Just probabilistically, this row 1, 3, 5, some of the bit will be flipped. Is that right?
Yes.
Okay, right. Please continue.
So yeah, as we have mentioned that our objective, the first objective that we have is to bypass the TRR mechanism. So there are two recent articles, Trespass and Blacksmith, which does that. So the concept behind it is that there must be a finite number of counters to keep a track of rows in those TRR mechanism. So that's why the authors of these papers introduced the notion of decoy rows. So we have two of these primary aggressors, those blue ones, and we have a large number of decoy aggressors, which we activate for a couple of times, and then we just ignore them to essentially fool the TRR mechanism that we are performing a row hammer attack. So after a certain number of tracks, the TRR mechanism is unable to track them, and that's how we bypass the TRR mechanism and cause a bit flip in the DRAM memory. So for this experiment, we need to profile the DRAM device. To profile, what we did is we performed a sweeping run. So we have 1 GB of memory space to us, where we allocated 256 MB block, a contiguous 256 MB block at some random address, say A. Say any random address which corresponds to a row A. So we selected two primary aggressors, A and A plus 2 while keeping A plus 1 as our victim row. Now we hammer it. Now in the hammering rounds, we access those aggressors A and A plus 2 5 million times. And then what we do is we increment both of these aggressors by 1. So A plus 2 hammer 5 million times, and then we increment A plus 1 and A plus 3 hammer 5 million times, and do this until we cover a 256 MB block. All the bit flips are marked on this map, and we generate a bit flip map. So on the right, you can see the bit flip map we generated by hammering a 256 MB block. So these white dots here are the places where we saw bit flips. Are you able to see them?
See them. I can see them.
Yeah,
So
yeah.
I assuming the aggressive row is somewhere in the middle, so you can actually see
we
that.
have not plotted the aggressor rows because it's actually difficult to put all the aggressor rows and the victims together. Everything will turn white since we are shifting all the rows by 1. But
right
here we did this in an extremely controlled setting because we allocated a 1 GB huge page first to guarantee us contiguous memory addresses where we can do double-sided aggressor attacks. The key observation here is that we saw 1742 bit flips in 738 rows out of 2048 rows. So this clearly states that some rows are more susceptible to bit flips than others. Clearly, there were 1310 rows with no bit flips in this case. So as an outcome of this experiment, we would like to assign confidence values to every row, where this can be represented by the equation here. Confidence of row R is equal to 1 by 1 plus the number of bit flips observed on that same row.
Okay, can I ask a question?
Yes.
Number one, when you do this experiment, you are putting aggressive row on every single places, so you can actually see which rows are more vulnerable to this kind of attack, or you actually only place aggressive row in certain location.
No, we put aggressor rows everywhere in that
Everywhere.
256
Okay.
MB block.
Okay. The second question is that for the same row, you said there is no bit flips. How many times you experiment performance, so the same action? What I'm getting at is that it's the same row. You actually try to do aggressive row right next to it 2,000 times. And for those 2,000 times or 20 times, none of the bit got flipped. Is that only, or how many times you actually did for each of the
I'll walk you through the experiment. So we selected 2 aggressor rows, and then we accessed those rows 5 million times. Okay. And then we shifted this row until we covered 2048 rows, and we repeated this experiment 20 times.
How many times?
20 times.
Okay, so it's 20 times. Okay. Yeah. So that's those 1310 row. They are not bit flipped. They are pretty strong.
Yes.
Because it actually survived 20 times, right?
Yes.
Okay.
So these are the initial results. So here, these are 2 more instances of the same experiment with different starting rows. However, you can clearly see on the right diagram that the number of bit flips are extremely less. And we suspect that TRR was able to effectively detect and mitigate all our attempts at flipping the bit.
Oh, so, I see. So when we're saying that they are strong, it could be TRR is helping to actually survive that. Well, how do okay, that's actually interesting. So for this 1310 row that's not flipping, is there any way we can actually check whether TRR is actually kicking?
Unfortunately, no, because DRAM manufacturers make the TRR implementation closed sourced, and there is actually no way of reverse engineering it, but only like looking at the outcome of what TRR is doing.
Okay.
So based on the yes,
yeah,
based on the
that's very
outcome,
interesting. Yeah.
those papers, the Trespass and Blacksmith interpreted how TRR must be working.
Right. Okay.
So for this initial experiment, we did achieve our goal to identify susceptible locations of the DRAM device, or at least a bank in this case. Our goal is to implement a page-based migration, page migration-based mitigation mechanism for pages which belong to the low confidence rows, so lower confidence rows. So each 4 KB page that we'll have on the OS will be allocated to a row with some confidence score, and we would like to allocate security and data critical applications on rows which have a very high confidence value. Other tasks which can tolerate some amount of data errors can be allocated into rows which have lower confidence values.
Hey, I have a question. When you do your experiment, I'm actually getting interested into this. So when you're doing your earlier experiment, you kind of shift your aggressive row. Everyone is like a 5 million, then you shift the next one, right?
Yes, yes.
What is the location of that shift?
Location
Meaning that you are just one row by one row, or you
yes,
actually do a jump?
one row by one row.
Okay.
So how this works is that when we access a particular memory address, say any address that we want to access, the whole row is activated here on the row buffer. So whenever you want to do a read or write operation on the memory, you have to activate the whole row.
Yeah. No, what I suggest, I wonder if you do the same experiment, you're getting different results. So I want to do exactly the same as what you're doing. Every row, 5 million SS, but I'm actually going to do the first row, then I'm going to jump to the 100th row, and then jump to the 200 and all the end. And then I go back to do the second row, and then jump 100 plus 2, and then jump another 100. So I kind of give them some time for them to kind of forget what we're doing, because I'm trying to understand how TR exactly try to detect whether if you're hitting similar region in a short amount of time, TR might do something different. So how confident you are about the TRR algorithm, the way TRR actually track and
so
kick in?
Yeah, our understanding directly comes from the previous works, and one thing we also have observed that if we keep repeatedly activating the same region over and over again, after some runs we don't see any more bit flips. So this was mentioned in the latter paper that if we keep on activating the same row over and over again for like a large number of times, the TRR mechanism is able to detect that.
Right. I think is interesting, but on the other hand, it doesn't make sense, because when I look at the graph you show, it's clearly being flipped. It's like in a particular area that's being like this one actually, you can see that is the bit flip is mostly concentrated on the middle area. But can you go to the next slide?
Yes.
In this slide, I see that the band of the white dot on the left side is actually on a little bit lower.
Oh, yeah, that's because of the starting row was different in those experiments.
Okay.
So on the y-axis, we have row numbers from 0 to 8192, and on the x-axis, we have columns.
Okay, interesting. Okay, sorry to interrupt you. Yeah, continue.
Yeah.
Okay, so this is a work in progress project. We plan on working on this project in the next few months. The result that you see will generate for one DIMM over a 13-hour run. We plan on reproducing the same run for a large number of times to generate concrete confidence values for each row. Once the profiling is complete on the OS kernel, we plan on modifying the mmap function. For pages mapped to low confidence locations, we propose to migrate them. Migrating pages for the OS is expensive. However, we are limiting migrations as we are using a confidence score for each DRAM row. Another approach to look at for this problem would be huge pages. Allocating a huge page ensures a contiguous block of memory. For high security and low confidence locations, such blocks of memories can provide several guardrails. This OS-based approach will be compatible with all the older generations and as well as the newer generations of DRAM devices, as this is primarily a software patch on the kernel. All rows have to be profiled, which can either be done at manufacturing time or during startup. Other than that, there are no further overheads. Therefore, this can potentially become a low-cost solution to the row hammer problem. Thank you.
Okay, thank you. I just want to follow up some of my question. By the way, what is the definition of a guard row?
If we keep some rows between the aggressor and the victim, you can only flip a bit on the adjacent, the
Right.
extreme adjacent of the aggressor row. So if we keep a few rows in between the victim and the aggressor, then the victim won't never get affected.
Are you sure it's adjacent row? Maybe
Yeah, so
two row.
There is a paper called Half Double, which was published last year by Google. So they have shown that you can actually jump at least by one more row.
Okay, there's a probability for jump one.
Yeah.
Okay.
Yeah. Apart from that, like if we keep sufficiently large number of rows, then we should not be able to do that.
That if people can jump two row, then the TRR is only refresh the adjacent row. Is that right?
Yes.
So that TRR might not be able to cover that behavior.
Yes, like since Google have shown that they were able to cause a bit flip there, it is likely that TRR could never detect it. They did mention that they use DDR4 DRAM devices because they use decoy rows to fool the TRR mechanism.
Yeah, I think this is a very important area. I think you guys are doing a great job in terms of try to tracking, where are the probability vulnerable about the row that bit flat. I mean, my fundamental question to your work is still, can I differentiate the physical property about the flippability about a row versus when TRR will kick in? Whether those, how do I interpret your result to be understanding whether it's really physical, that row is less vulnerable, or actually TRR has some implementation that's actually be artifact to what you're seeing. So I naturally I'm thinking is that for your experiment, instead of going like one row at a time, like you shift your aggressor row, you actually go to a different pattern, which is you kind of jump a little bit and see if the result of the row flip, whether it's going to change significantly, or if the result is more or less the same, then it doesn't matter, right? Then basically whatever your result getting is, but if you see a significant difference because you're running experiment, then that's very interesting, because then we can actually see that there are certain behavior is going to trigger TRR differently. By the way, I remember you talk about the difference between DRAM 3 and DRAM 4. Is that right?
Yes.
I remember. What's the main
Yes.
difference? Are there any difference in TRR implementation?
So DDR3 doesn't have any TRR, and DDR4 devices have this TRR mechanism. So the reason why they put this DRR mechanism is because DDR4 are way more susceptible than DDR3 devices because they are denser.
Oh, then that will be interesting. have you performed experiment on DRAM 3?
Yes, we did. The number of bit flips were extremely low because we kept it running for, I think, almost a week to see how many bit flips we get. But it was, I think, around 100 and something. And this is like the results that we showed here were runs after performing experiments for 13 hours. So there is a significant increase in the number of bit flips.
Okay. So basically, okay, but with DRAM 3, your experiment, did you actually see there are certain area that's actually more flippable than other area?
Yeah, we did not look into the maps of DDR3 devices, but we will, yeah, we will certainly take a look into that.
And have you tried two different DRAM,
DDR4 devices?
DRAM, two different DRAM for exactly the same configuration, whether, I'm just trying to understand whether physics property, say two DRAM 4, exactly the same chipset,
Yeah,
are they
so,
going to show similar behavior?
both of them will definitely show bit flips because bit flips, the theory behind bit flips is that during manufacturing process, the variation for every single DRAM device will be different. So in theory, we should see like bit flips, but maybe the number of bit flips will be a little bit more or less. But it is again, like there is an element of randomness into
Right.
it.
No, I understand. If you have a
Yes.
randomness, that's actually good news because we know that we can detect for each of the chip what is the area. But what I'm saying is that if you use your algorithm one row at a time, aggressor, one row at a time, and if two chips, two DRAM 4 chips, the band of the white dot are still similar to each other, that means we know it's not physics, it's actually TRR. But if you look at the DRAM 3, you do two different chips, and because there's no TRR, so they're supposed to be more different. So using this, you might be able to answer, not completely, but get some better answer about whether it's TRR. I'm still interested in that issue, whether it's TRR or it's just the physics, the randomness of the chips. Yeah.
Yeah, maybe we'll also take a look into that because we need to differentiate between the TRR and the variations, and that is one of the things that we are also trying to achieve.
Okay, that's good. I think I asked enough question, and
Okay.
I need to move to the next group. But I think I feel that if you keep doing this, this will be extremely interesting result for to answer some of the question that raised by Google, and I think this will be a great academic publication that you guys can work together. I think this is a very important topic, and once this work is clear, then we can actually think about, well, what can operating system do to actually be able to mitigate this at the software level. my feeling is that if you have all the facts about how TR really affect DRAM 4, and how is the different region, I think you can come up with a very nice result because I can use a software try to trigger some of the refresh like a TRR on top of TRR. And I think that will make the attack space much less to happen. Yeah.
Yes.
Okay, that's perfect. Very impressive about the work. Very interesting.
Thank you.
Oh, thank you for your hard work. Okay, all of you. Okay, the second group, I saw Lyndon come back, right?
Yeah, right.
Yeah, you can please unshare your screen so the second team can actually.
공유하게 하면 될까요? Can you see my screen?
Yes, I can. Thank you.
And I'll start our final. I'll start our final project presentation. Our topic is optimizing distributed storage system in the home edge network. And here are our team members. I'll explain what edge computing is first. Unlike conventional cloud computing, edge computing processes data immediately at the location where data is generated. It can improve processing speed by reducing the time for transmitting and receiving data from the cloud server. By configuring an internal network, edge computing can quickly process data. We developed a storage system specialized for data distribution with unoccupied storages of IoTs in small home network. By spreading data to the other IoT devices within the home edge network, we can use storage efficiently. Using our system, we can use the storage of devices belonging to the same home edge network more efficiently. However, here's a key issue of our storage system. If one of the IoT devices that has a part of the file does not work, it would be hard to recover the original file. But we can think of the following facts. First, since most of them are home appliances, we can easily get them back on track. If important data needs to be backed up, we can use an additional file system such as NFS. I will show you our use case demo video. In order to demonstrate the use cases, we run one edge server and 4 IoT devices. The red tab in the terminal shows the edge server and the IoT devices are shown in the blue tabs. After the IoT devices are off, enter the port number to register the device with the edge server. Check if all of those devices are registered. Now we can see that all devices are registered with the edge server. And I'll distribute the file in one node to the others. Before uploading part of the file to each device, confirm the connection between the edge server and the IoT devices. If the server is live, go on to the next step, uploading metadata of the file. The first IoT device uploads the metadata to the edge server. If the metadata is uploaded successfully, we should check if the IoT devices are up and storage capacity is enough. We can see the storage information and whether the IoT devices in the home network operate well. The first IoT device received the information about the other IoT devices from the edge server. The first IoT device now uploads the file to the other devices using information received from the edge server. After splitting the file of the devices, distribute the file to each IoT device. Here, the first part will be stored on the first IoT device, and the rest of the file will be stored on each device separately. I'll show you the second use case, the file download part. Like the previous scenario, there are 4 IoT devices and 1 edge server. In the previous file distributing use case, a piece of the distributed file is stored to each IoT device. The first step for downloading a file is also checking if the edge server is alive. If the edge server is alive, the IoT devices send the request to get metadata of the file. Edge server verifies the metadata and checks if the metadata-related IoT devices are alive. And the Edge server receives the sequence of parts, the hash value of the file, and the connection information of the device from each IoT device. And the IoT device which is ready to retrieve the file receives the information of the device from the Edge server. The Edge server gets the part of the file data that each IoT device has and merge parts of the file in sequence with metadata. Finally, check if the hash value of the merged file is the same as the hash value of the original file. If there's any questions, please ask us now.
Professor, you're muted.
Yeah, thank you. I think I got a pretty good idea about what you're trying to do, but just validate. So what you have is that for each of the IoT device, their data, in some way you distribute copy your data to some of the other IoT device in the same home network. And if one of the device, say this device, I'm actually was not working, I have to reset, then I basically can go to other IoT device to retrieve the data that before my crash or before my failure, and through the help of the Edge server. Is that pretty much summarize what you're doing?
Yes, so the Edge server has the metadata of the files, and if the IoT device wants to retrieve the file first, they will ask the Edge server to get the metadata, and when they see the metadata, they can see what IoT device has each part of those files. Then they can use that metadata to ask the parts of the files from the other IoTs. So that IoT can get the complete file by that way. So it's distributed. However, the Edge server has the metadata.
Right. So here's some of my question. For example, you're talking about home network. So let me just use some real example to clarify. So assuming in my home, I have my refrigerator and my say my TV, and then my whatever the some kind of monitor, the surveillance device. Assuming I have another one, which is maybe a music server, a music sensor, or whatever, or Google Home, this kind of device. And then I have my Edge server is connecting all this four. So so we're talking about you're going to duplicate some of the information about your refrigerator to my TV, my surveillance system, and some of my music service box. Is number one, is that true? Is that we're talking about is duplicate one particular place to the other three?
So, for example, if the refrigerator has some data file,
right,
it can speed up the data file into 4. At the beginning, the Edge server got the registration from from those 4 IoT devices. So that means there are 4 IoT devices, and then the Edge server is going to upload the file and to split the file into 4 parts. Each of those IoT devices can get each part of the file.
Okay, I think I want to clarify this, Lyndon. Is refrigerator considered one of the IoT device?
If it has the the network card, it can
Okay,
we
yeah,
can
no, I
even,
assume they all connect. They all connect.
Okay, yes.
So which means that each of the devices, so any of the home network IoT device, when I say IoT device, I really mean those appliances with the IoT capability at home. So means that each of the appliances, they need to have some storage to serve in the process, right? I have to reserve certain kind of SSD memory to be able to save some. Okay, that's good. Okay, just for clarification, I think that makes sense that you're actually doing this kind of data replication to actually preserve the almost like a backup, because the what do you call that? The edge server might not have enough capacity. Usually the other way is we just store our data. We trust the edge server to be more reliable. So we just actually store the copy of the information. But what you're suggesting is that maybe we want to support each other. Okay, but here I think is an interesting scenario, which is, this is not a question, but it's about scenario I'm actually thinking. So I'm at home and I have my smartphone. So I'm at home right now. So I actually download all the data from my IoT. So this IoT could be my refrigerator information, or could be my TV information, or could be my music, whatever information I have. Now this is on my device. So I'm actually keeping some of the information. Then I'm actually going to the other location. I walk into the other person's house. This could be my my close friend's house, and they have actually a IoT network, a home-based IoT network there. And assuming they authorize me to be able to access, so now my phone become part of their network as an IoT device. So this actually become really interesting, because now I can actually pass some of my information to their IoT network, and I might be able to do some application, utilize that information. Do you think this is a possible for the environment that you're talking about?
Yes, I think that would be possible, but you can only do the uploading, because if you want to download a file from your friend's edge server IoT devices, you need to have a piece of the file or a part of the file. So it would like to do like the authentication mechanism. So you can only do the uploading, but you cannot download the file from your friend's server.
Oh, it might be possible. I can tell you why. It might be possible at some point. Let me actually tell you the scenario I'm thinking about. For example, we're actually two family. We're going to serve a 200 say homeless people about a meal over Thanksgiving. So essentially all the food we have, some of the food stored in my fridge, some of the food stored in, say, Inkai, assuming you're my friend, we're going to work together, you have a fridge. So some of the food is going to store in your place. And you're actually going to buy some new food. And I'm going to buy some new, but we like to keep the information, both the content of your fridge and my fridge. So essentially the information from both sides are important. So one of the idea that we might be able to do is that you actually have your phone at home. I have my phone and my home. So what we can do is between our phone, we can actually build up a channel. So I can actually allow your phone through my phone to access my fridge information. So you actually be able to put the whole thing together to understand to update that. But the thing is, when I visit you a day before, I already upload some of my fridge information when I go there, but I can also do some kind of update over there. So I'm actually just thinking, this is of course beyond what you're doing, because what your project is doing is really try to do what I call a data replication or data backup service over there. But through that scenario, since the data can be distributed among the IoT device, and I consider my phone is also could be part of that IoT device, meaning that I can actually participate, means that I will get a copy. And in that sense, I'm actually thinking this could be even more interesting because I can do some kind of backup across multiple home network, which basically say if your home is got a shutdown or got destroyed and all your appliances are gone. But don't worry, I actually store one copy at Inkai's family. So I will be able to get it from your network to be able to do that. So I'm just thinking that that might be a scenario. I mean, the motivation I really have is that, well, how do I actually be able to share information about our home appliance to somebody we trust? And maybe this two information putting together might be able to help us to actually do some interesting application. Yeah, that's just my comment. That's okay. Yeah. Okay. Do you have any question or anything you want to talk about?
Yeah, I have some comment about your case. So in your case, there are multiple ways. Some traditional ways, we can use SH, secure SCP, or using VPN. That's one traditional way. And also we can use the cloud. That's the other way, a more latest way. But we will go because we will go to cloud or the cloud. So the home, this is the home network one, and go to the edge server and go to cloud, and then go to the cloud, go to the other edge server and the other network. So that's the second way. Also the third way, you can ask people, if you consider the humans as the intermediate agent between those, you can just let the owners of the both network to just talk to with each other, so they can build some personal agreement. So make sure they have their own secret channels. But so that's basically your idea of the interdisconnect network by the human agents. So
Right,
that's a
right.
three-way possible way to do that.
Right. That's true. I mean, obviously, my preference is go through the third way, because
Okay.
the first two way first way, anything go to the cloud, I might be worried about the privacy, about the home network information. Yeah. So that's why I'm thinking that some of this we might use as you mentioned, the third way for us to connect together. Okay. Thank you very much. Thank you for your work. It's very interesting. So can you unshare your screen so we can move to the next group, right? Thank you. So we have another group, right? Naveen and Sai Vivek and
Vivek,
Sunny and Rashbat, and you're the same group, right?
No, Professor. Actually, me and Naveen are in the same group. But we are supposed to present at 3 o'clock. Unfortunately, we were in the other link that was there on Canvas. We confused it with this.
Okay, that's okay. That's okay. Can we do this? And which group is still here? Let me see.
Yeah,
You
Professor.
and Naveen is one group, and Sunny, you're the same group with Rishpa. Sunny is everybody from your group here already?
Yeah, yes, Professor. Rishabh and me, we both are in one group.
Okay. So may I ask, what is your topic, Sunny?
It's distributed social network, Professor.
Distributed social. Okay. And Sai, what's your topic?
Our topic is privacy first query optimized horizontal partitioning.
Oh gosh, both of them are interesting. Okay, we have to flip a coin. Which one go first? Okay. Yeah, I mean, I let you guys decide. Whatever you want to go first. Whoever want to go first.
They can go first, Professor.
Okay. Yeah. All right. Thank you. Thank you so much, Sunny. Okay.
Thank you, Sunny.
Yeah, thank you, Sunny. Professor, let me share my screen.
Sure.
Professor, you're able to see my screen, right?
Yes. Yes.
Good evening, Professor. This is our project. I and Vivek worked on this. Privacy first query optimized horizontal partitioning using k-modes. So let me tell you the problem statement. So when there is a large data set and when there are like huge number of queries executing on them, traditional query execution will bring the entire data into the memory, which is a bit less optimal because it leads to a lot of IO operations and the results obviously will be slow. So to address this problem, the traditional methods that are used are to bring vertical partitions to partition the data. So partitions based on the columns that are frequently queried or can be clustered on the disk to increase the IO throughput and to improve the query results. So this is what happens. But is that enough? Can't we do more? So consider this set of queries, Professor. Suppose a large set of queries come on a column that is the years. And if the columns are specifically targeting some years, say suppose the queries are many queries are targeting the years some 1920 to 1930. So it is not optimal to bring entire set of the entire data query, the year data into the memory. So what can we do here? So we introduce horizontal partitioning. So because it improves query responses, but how do we select which data to partition horizontally? How do we select how do we improve upon it? How do we actually do horizontal partitioning and decide the criteria based on which we have to do this? So this is our solution. Vivek, can you go through it?
Yeah, thank you. Let me share my screen.
Okay.
Is my screen visible, Professor?
Yes.
Yeah. So as we said, as Naveen has already explained, in our project, there are 4 critical parts. First is privacy. So we integrated the whole design of a system with privacy first design. What do we mean by that? So let me just start with a quick demo. Okay. First is in our entire design, we have multiple steps to do. The first one is pre-process. Like whenever we have the data, we have to first, like whatever CSV we have to pre-process the data first. Then from that, we need to train it. We need to do train on the specific data to create a model which can predict which partition the future data that is going to come. So the initial data that we took was something like this, names CSV. It can be any data, but we took this data because it is easy to run and easy to create partitions on this data. It has names like Mary, year, what is the gender, what is the state, and what is the count. Now all these details are there. Now, and also we have taken like certain queries, we have written ourselves like a certain set of queries to train our model to extract the predicates from each query. So after having these queries from here, what we did is we extracted the predicates from each query. So like state is there, name is there, and we created a column list, which is nothing but which will have all the columns and which will give like ones and zeros with their specific place. So it is a categorical data that we have for this particular problem. From this categorical data, what we decided to do is we decided to use a clustering algorithm because it's a unsupervised learning problem, machine learning problem. So we used a k-modes clustering algorithm to decide based upon the value list which we are getting to which cluster does it belong to. So based on that, we created the training. We created the training model, and this is how our training model will look like. It'll have its own generate model and training partitioning. Now, after that, we will go into the post-processing step where we will store all the partitions. Like we'll store the metadata for the partition. And after this, our primary step for us to is like build the partitions. So the post-processing will generate like what kind of metadata we need for building this horizontal partitions. And finally, the build partitions will generate the partitions on this metadata. So first, I've taken a small data set. It actually works very well for huge data sets, but for the sake of presentation purposes, we have taken a small data set to show you. So main.py. So now this, like initially, I'm going to delete my previous partition data and metadata, part metadata. So now by running this will essentially create all the partitions. It has already done all the other steps. As you can see here, this is the training process, generating the training data, because we need to pre-process the data, right? And then it does the machine learning step. And after the training is complete, we are starting the vertical partitioning and then lexicographic partitioning. So there are also two types of partitioning that we have followed. Now, for suppose in a column, if there are more than 200 unique values, right? It is not very logical to partition on every single value that is there in that column, because that will essentially create a small file problem. So to avoid the small file problem, we have decided upon two strategies for horizontal partitioning. One is lexicographic partitioning and one is value-based partitioning. In lexicographic partitioning, we'll have, for example, let's say there are names. Based upon the name, like each alphabetical order, lexicographic order, the partitions will be made. And if at all it is the values are less than 200, we'll do a value-based partitioning where we'll get it based upon the different values that we have. Now, this is the partitioning data. So I'll also show you the metadata that got generated. So this is the metadata that got generated to my array. So the first one is like a vertical partitioning data. Like if at all the data is, let's say, a flat file in a CSV, from that first we are creating a vertically partitioned data set. That is my first cluster ID. Now, apart from that, this is the second one. So I think I should also show you what are the predictions. So part calls are the predictions that were made by the clustering algorithm. So it said like, so these are the things that you should cluster on name, year born, and year born, because I think it has some bias towards it. That's why we got year born here. Maybe we would have got something else if at all we tried it again. And in the next partition, we have this cluster ID, like where year born. And since the number of values in year are less than, I think less than 200, so the lexicographic partition doesn't happen here. So that's what each of these values mean. Now that like we have all the partitions with us, we need to build a query engine on top of it. Like we can't do anything with the data that we have without a query engine on top of it. So that's where we created another query engine and a query interceptor. So the query interceptor, what it will do is, like whenever a user queries the database, it will intercept the query that is coming onwards, and it will edit the query to go and hit that specific partition which it was meant to hit. So we'll parse the query and we'll see which partitions is it efficient to go and hit, and it will hit that partition only. And I will now Python run main.py. I've also told you like it is a privacy first design. Like for example, let's say there are few columns which a user is not supposed to access. He will not be allowed to do that query. And if at all the user has like entire access, then he'll be able to do that query. I'll demonstrate that also that as well. Now, Python main.py. So first, I'm going to enter a username that is not there in our users list. It's not there in our users list. Let's say I'm going to enter Sai. So it will say invalid username. So you should enter a proper username. Let's say I've entered Vivek. Now Vivek has only access to name, year born, and count. He doesn't have access to other columns like state or city, something like that. He doesn't have access. Now, for example, he tries to do a query like select star from df where state equals to California. So it will straight away say that you don't have access to the state column, so you cannot query this particular data. Now, let's say we do have a query and we do want to do it. So let's say select star from df where year born equals to 1910. So now we have entered the query. After entering the query, it is just going and selecting what are all the partitioning that is there. And finally, these are the query results. I haven't created a very good statistics file to show you the performance of this in the query. But what we have done is we have created another stats compare.py where we'll compare the execution time using a flat file CSV, using the vertical partitioning, and using a automated partition that has created by the machine learning algorithm that we've created. So the query is like select star from the DB where year born is 1910. Let's say this is the query that we are trying to do, and we wanted to compare the stats. Now, if I do Python stats compare.py, now here we can see the difference in a clear fashion using a direct CSV. If we do the query, the time taken, the execution time taken is almost like 0.23 seconds. But using a vertically partitioning, column-based partitioning Parquet format, the time taken is 0.21 seconds. But using the horizontal partitions that we have created, the total time taken is 0.02 seconds. It's almost a 10-fold increase in performance because of the partitioning that we have taken. There are a lot more complexities involved in this project. Like we have built everything in a custom manner. We've built our own SQL parser to parse the query and make changes. Yeah. That's it. Any questions? I'm sorry if you're not able to explain it the best way possible, but
no, it's great. I just want to tell you that there was lots of questions in my mind, but I want to start it with something which is I have been doing for the past 5 years, about horizontal partition, which I'm doing this manually, but your work is a lot cleaner, I think. So what I did is I'm analyzing the Facebook data. And within that Facebook data, I have about 2 billion users. So you can think about have a SQL table, which was 2 billion entry. And I mean, how do I actually be able to, anytime I do any kind of work is you can think about 2 billion is really hard for me to do that.
Exactly.
So what I did is I actually duplicate that table into another 26 table. Actually 27. So I actually say anybody named with A, B, C, D, E, all the way to Z, and there is a lot of international name, which is actually a special character I put into the other table. And obviously mine is not optimized because the R table, S table, T table, they're the biggest.
Yeah.
The RST, they're the biggest. And like a Q table, Z table, especially X table is usually the smallest. So the thing is, the work is very important for us to be able to handle the performance you want to get by so otherwise it's impossible. So here's my a few questions I have is that number one, when you do this partitioning, do you allow this partitioning to be overlapping? So means that I could have a partition which has A and B, and the other partition has B and C.
Yes.
It depends on the query, right? Yeah.
Yes, exactly. So it depends upon the query. As of now, we are only taking the mode. For example, let's say in the 10 queries, whichever value, whichever predicate has the highest occurrence, we are taking that as a that as a base for partitioning. But our idea is to extend the partitioning to as much level as possible. Because the K-modes algorithm that we are using, when it predicts the output, it will give a list of values, like something like it will give, for example, let's say there are 5 columns. It will give 0, 1, 1, 0, 0 as an output, right? That means we have these 2 values that we can partition on. And we also created a map which will contain the partitioning of this particular thing, which will get generated automatically. For example, if we can see this part data, right? In this, it says here like partition by, and it's a list. So it will have what are all the things that it has. Now we can delve deeper, like inside a name partition, we can have an year partition. Inside that year partition, we can also have multiple other levels as well. That is also possible, but we haven't implemented it yet. It is possible, and we wanted to implement it.
I see. So the other question, before you do the demo, you show me a slide which is essentially every line is a SQL line. There is a one slide or a screen, I forgot, or maybe it's a file. Yeah. I mean, I saw a lot of yes, this one. Can I actually take a look at that?
Yeah.
So I assume this is generated by unsupervised learning.
Correct, Professor.
Okay. So this is generated by K-mod.
Yeah. So this is the training data for K-mod's algorithm. I can, yeah. Meanwhile, I can show you a small demo for that as well. Main.py. Yeah. So we have a thing called Predicate Extractor, which will extract the predicate from the query. Now, let's say my from predicate
Predicate spelling is wrong, Vic.
Oh.
Not there.
No, the query is PRE.
You said
PICATE.
Yeah.
Now it's right.
And you have written form also instead of from.
Yeah.
In the console.
From predicate extractor, import predicates.
Is it from or form?
From, yeah, it is correct. Now for this, let's say I'm giving a query equals to select star from DF, where year born equals to 1910. And 1 second, this should go in double quotes. And name equals to Felix. Let's say this is the query. Now, if I send it to the predicates of query, this will generate a predicate object. Now, this predicate object will have something called a training data. Now, it says there is a column map already with me because I know what the data was. So I have a column map. From that metadata of that columns, this is the columns.json. So here we have name, year born, gender, state, and count. From that, we got since this we have extracted the predicates, like year born and name are the predicates that we extracted. So the column map has got this 1, 1, 0, 0 as this. Now this we have let's say there are some 200 queries. Let's say we have. Now it will generate this kind of predicate list for all these 200 queries, on top of which we'll perform k-modes clustering algorithm. So the k-modes will tell which thing will go into which cluster and what is its metadata, what are the columns that this cluster will have. So based on this, we will in future use the same thing to the same model that we use here to predict the cluster where the query has to go to fetch the query results. So this way it's very optimized. That's why the privacy first, query optimized. So we are optimizing the query to go to a particular place based upon the previous queries that we ran. So that's why it's kind of a smart way of doing it, is what we thought.
Good. I think I probably need to follow up with you because I have a data which I have been using manually. I'm really interested to see if I can use your methodology to be able to find out a better optimized way of query and try to see how fast I can do. By the way, are both of you or either one of you a student working with Satucci? Muhammad?
No, professor, I'm not working with him.
Okay. So how about you, Sai? Who you're working with in your? Are you a PhD student or master student? Just
I'm a first-year master student, professor.
We're both first-year master students.
Oh, welcome to UC Davis. Yeah.
Thank you.
Because Professor Satucci, his specialty is database. Oh. So he's distributed. I think at least one of the students in our class. And that's why I thought maybe he's supervising this part of work of yours. Yeah, I'm very interested in what you're doing. And maybe after the winter quarter, I will try to contact you and see if you're interested to discuss about a really big data set that, by the way, with that data set, I'm doing SQL all the time. And sometimes when I run the query, it's one day, just one day. To do, I mean, it's the number of reaction, the I need to process is about 10 billion. It's a table of 10 billion entry. A comment is smaller, so that's why we have to do this partition a lot to be able to do something more efficient. Otherwise, run a major query is easily take days to finish, and if we're lucky, yeah.
We would love to work on such projects, Professor. We're also this was I think we spoke last time. You gave us the idea of using multiple places. So from there, we both sat together and designed this whole system so that it can accommodate maximal cases as possible. Oh, so we would love to work with you if there is a chance.
Oh, that would be great. That would be great. Thank you, Sai and Naveen. Just a quick question, Sai. I mean, your first name is Sai or Sai Vivek?
It's Sai Vivek, but
Sai Vivek. Okay.
Yeah, Vivek is what
what he prefers, Professor.
Yeah. No, I will call it. I have some friends. I usually call them Vivek. So I assume Vivek is a first name, but you have a Sai, so I'm not sure. Maybe Vivek is your middle name or something. I'll call you Sai Vivek. Yeah, Naveen, I can handle that. That's easy for me. Okay, so thank you very much, and I think you should unshare your screen. We should move to the next group. Okay, I'll contact you later.
Thank you, Professor.
Have a good day.
Excellent.
Thank you, Professor. Have a good day.
You too.
Have a nice day, Professor.
You too. You too, Naveen. Hey, Sunny and.
So can we proceed? Hello, Professor.
Hi, Professor.
Hey, how are you?
You're good. I'm good.
Okay, so it's your floor is yours.
Thank you. So let me share my screen. So are you able to see my screen?
It's coming out. Oh, distributed social network.
Yeah,
I can see that now.
Okay. So this is our topic. I am Rishabh and that's Sunny. So let's dive in.
Hello.
Hello. Yeah.
Yeah.
Hi. So the motivation. The thing, the reason we are focusing on this is right now, there are so many social networks out there, but all of them are divided. There is no unity. And even if we are looking at one specific giant network like Facebook or Instagram or any other of these giant networks, they don't cater to everybody's needs. So the idea is to have your own network or connect to the network of your choosing, and you don't have to feel left out. It's not like just because you're not part of the bigger network or you don't sign up with them, you're left out and you can't do stuff on your own. So with that, what we want to present is a social network that caters to every community's needs. So whatever specific details that you have or the specific features of your community, you can have them implemented in your network. You can have people access that and still connect to people from other networks as well. So it's not just restricted to your own community. So what is happening right now is there are so many small apps, social networks that focus on particular groups. So there are applications for travelers. There is an application for app for people who love food and all that. But these aren't interconnected. And if every time I want to see what's happening in a particular community, if I have to download an app, have a sign up and all that, it results in so many subscriptions and so many signups. So we want to solve that as well. So the problem statement. What we want to have is a universal message passing protocol. And anybody who implements this protocol will be able to access the whole of the network. So you can have smaller sub-networks, we can call them as sub-networks, groups, communities, which implement this protocol, and they can connect to every other community which implements this protocol. So that is the problem that we are trying to solve. Now, current social networks aren't, you can't operate between them. There are no regular one standard for all the networks. So those are the important problems. So we propose an architecture for a distributed social network, which is built on a universal standard. And so yeah, that is the problem statement. Okay, so I'll start with an introduction. And so every particular application can build its own network, okay? And they will be able to access other networks. Regardless of which server one particular user is connected to, they can interact with others from different servers. So the example for this is, there are some distributed networks that are there right now. So Mastodon, Fediverse, these are certain distributed social networks which are there right now. So the basic structure for them looks something like this. So you can see that there is one particular microblogging platform. There is one image sharing platform, and all of these are connected by this activity pub. So so that is Fediverse. This is Fediverse distributed network. So they have different applications or different services, to be precise, and these services are interconnected through a particular fabric. So this is the implementation right now that people have.
Yeah, the only one I am familiar with Diaspora. That's a long time ago, Diaspora. I don't know whether it still survive or not. I don't think too many people using Diaspora anymore. Yeah.
So they just used that as an inspiration to come up with this. Even this isn't being used as globally as they would have wanted, but there are some future. We would like to discuss the future work part as well. So where we can comment on the.
May I ask this question? So, for example, in this picture, you have one circle called peer tube, and then next to peer tube, you have something called fleroma, right? Those two. What's the circle? What's the blue circle? Each of this represent a component of a one single distributed network by say Mastodon or something like that.
So Mastodon and Pleroma are the microblogging services. So it's like separate services. So they have, so if you think about that as a particular class, then this has some of the audio and video streaming functions. This class has some of the microblogging functions, and all of them have this common activity pub function which connects them.
So they are from two different providers.
Yeah.
Okay. Yeah. And then how do they interoperable?
So that's this activity pub fabric that Fediverse provides. So if you are able to, if you implement this activity pub in your whatever network you create, you'll be able to access everybody who uses this activity pub.
So that's what you call Fediverse, right?
Fediverse is this whole network. This whole group is Fediverse.
Okay. So it's like, so the activity pub is defined by which company? Fediverse?
Fediverse.
Yeah. Okay. So they provide the interoperable.
They provide this all. Yeah.
Okay.
Yeah.
Okay. Well, I didn't know this. So is any of the major US social media using Fediverse?
No.
Okay.
No, because it's exactly opposite to what they want to do.
Right.
Because
they don't have an
this,
incentive, right? They don't have an incentive. I mean, Facebook definitely don't want to use Fediverse.
They want to have the complete control. They don't want to distribute anything.
Yeah. And, but that's exactly what we don't like.
Yeah. So that's the motivation for doing all this. I mean, because they are able to comment, I mean, have so much control on the content that is being shared that they can ban people. They can, do all like even elections. They can even manipulate elections. So that's how much power they have. So moving ahead. Okay. So Sunny will explain the implementation details that we have.
Okay. So moving on to high level implementation, I just want to give like brief description of what we are planning to implement. So basically each circle here denotes a platform, separate platform. And for example, let's assume this is an image sharing platform and we have an event planning platform. And there are multiple platforms like that in our network, which are hosted in our network, and each platform will have its own users. So what happens is whenever a user sign up with any of these platforms, these sign up details will go in the form of sign up messages to the queue storage. And then this queue storage will send these all sign up messages to all servers in the network. So basically this queue storage will distribute the sign up messages to all servers so that each server can maintain a client log, which has the client server details of all the users. So this is basically we need this because to maintain consistent and reliable user data in all the servers, irrespective of the platform they are using. So for example, let's assume that image sharing platform is using a server A, and there is a user in that platform called Sunny. And if I want to connect to a person from different platform, what initially this network does is it creates a virtual server which identifies my identity and it has my private data. So this virtual server will connect to the other virtual servers which have the identity of the user that we want to. So in this way, we will cross communicate between the platforms. So this is our high level like implementation that we want to use. So every server can create instances of the user that stores their identity and data. And each instant can be used to communicate with other identities from different social media platforms.
May I
So,
ask a quick question, Sunny? So when you have in this picture, you essentially have 4 different platforms.
yeah.
And I assume that if I want to access, I have to have signed up for each of them. I need to have.
But
I need to have an account, right? Have a user ID in.
Yes, you can have an account in any one of the platform. That will be enough to communicate to any other platform that you have. That is the main advantage of distributed social network. If we need signups to every other platform that we need to communicate, then it is no different than what we are using right now.
Right.
So
no, the thing I'm actually want to ask is that I guess the question is, if I on one platform, would I be able to seamlessly integrate some of the content I share in another platform? So for example, right now, each of the platforms, some is image, some is video, messaging. So I might actually do a messaging, but in the messaging, I include the content of the video that's actually from the other platform. I assume that's actually okay, right? Or it's not possible.
It is okay if these all platforms are hosted in the same network and have the same protocol, same universal message passing protocol.
Right, but that indicate that there is a mapping, because say the video belongs to Sunny on the video blogging platform, and also the message is belong to another Sunny, which is under this platform over here. Which I like to do the following is I would like to do a linking between these 2 accounts, and such that anything that's happened in the video will automatically get shuffled. That's what I'm asking, whether that's actually possible in this platform, or that's actually a goal or not a goal in your design.
Yeah, that is actually one of our goals, Professor. And actually, if we go forward, we can see that in applications of this project, we have taken one simple example that, so for example, there is a video in video sharing platform, and there is same content in the different platform that you're seeing, and you're commenting on that video, and you want that comment to reflect on the other platform as well without having sign up to that platform.
Right, without having signed up, without having to share, right? It will automatically do this this mapping. Okay,
So
good.
that is what we confined into activities that we can do within this network. So the user relationship between the platforms and the activities that they can use is one of the things that we have concentrated. And this is high level implementation. If we moving on to the next slide, we can see a detailed design. Rishabh,
Sorry.
Okay, so moving on to the next slide, we can actually see the detailed design. We have only considered only 2 servers right now for practical purposes. So for example, client server 1, let's assume it's a video sharing platform, and the client 1 is a user in that platform, and he wants to send a message to another client who is hosted in a separate platform, different platform. So what we do is we send a message giving the client ID and the message that we want to send. These details will go to the server, and server will have a client log. This client log, we discussed earlier that this the sign up queue that we have It is used to share the client details across the servers, and each server will have this client log, which has all the details of server client. And this detail, from this details, we can get that, okay, client 2 is in server 2. Then the server 1 will contact server 2 requesting access token with, for example, here I'm using the basic mechanism that is used in current social media platforms, that is API. But Fediverse actually uses network key instead of API key. That's more universal. And we give the API key and our credentials. Those will be authorized in server 2, and they will give the access token to us. And using that access token, we will send the data from server 1 to server 2. And now the server 2 will send the data to the client that we have requested with the client ID that from where the data is coming from. And it will send back the acknowledgement all the way back to the client 1. So this is the detailed design of what we want to do, like between cross-platform communication. Yeah, so basically whenever the client is created, means user in any platform is created, then the entry is recorded in client log and it is shared onto the queue. So the clients from other server are visible to each other, and the clients can contact each other to respective servers. So this is the design that we are trying, Professor. And moving
a question.
Yeah.
What is the difference, do you think, between your design and Fediverse?
Yeah. So the main difference is we are maintaining a client log in each server, Professor. And Fediverse, I don't think they are doing that. And we got this idea from actually transactional ledger, which is used in blockchain. So basically we are updating all the servers in a distributed way so that there is a consistent data in all the servers at all time. So that is what we are trying to achieve here. I don't think Fediverse uses that. Fediverse puts a constraint on platforms that each platform has to integrate with their activity pub. So that's one constraint that they have. So we want this to be more open source and more open to the other platforms so that they can easily deploy and communicate with other platforms.
Yeah, I'll tell you later about what I'm thinking. Yeah, please go ahead. Yeah, it's very interesting. Yeah, go ahead.
Okay, moving on to the next slide. Yeah, this is the same thing that we have seen earlier. This is just a sequence diagram of how the data is flowing. We'll send the data to server. It will check the client log. It will then authorize the details and establish the connection. We'll send the data. We'll get the acknowledgement. That's it. There's not much to talk about here. So yeah, now I think it's time for the demo. I think Rishabh will show the demo.
So I'll show a quick demo. Okay. So I'm going to start the second server. So this is a microblogging site. And then we have another one. It's a photo sharing site. Now I'll run the first client. So this client, what this client does is it actually belongs to the first server. And this client wants to send message to the second server, client 2, which is part of the second server. So when I run first client, the message goes to the first server. It requests for a token and sends this message to the second server. Now, when I run the command for second client to read the message back, so we see that it got a response from the second server saying client 1 says hi, and this is the timestamp. Okay. Now, when we stop these servers, there are certain information that I wanted to share. So when I stop this server, this is the first server. It says the profile dump. The profile it has is of ID client 1 and name Rish and age. So this is the only profile that this server has access to or visibility to. And if you see the client log dump, it says client 1 is part of the first server and client 2, the URL of the second server is given here. And similarly, when we stop the second server, we get the same thing. And second server only has this profile information, that is name Sunny, ID client, client 2, and the respective age. And if you see the client log dump for this one, it has client 1 at 8383 and the client 2 is the second server. So this is basically the server ID that we are using right now. And this is how the implementation looks like. So with this, I'll go back to the presentation. And so yeah, now we can talk about the applications. Just a moment. Okay. So what the application is, as you said, you had asked, like, how is it different from Fediverse? They have this activity hub that they have to implement and stuff like that. Now, imagine right now in Web 2.0, what we have is there are some internet protocols, HTTP protocols that websites can implement and they can connect to the whole internet. Now, the next thing that is going to come is Web 3.0. So with that, what we want to do is everybody should be able to spin up their own social networks or create own content, have people belonging to their belong to their server and still be able to communicate across. This universal protocol, if anybody implements, it will be like small LANs in internet where, but instead of LANs, you'll have your own social networks there and you can communicate across the globe and have this universal reach. And one protocol for Web 3.0 kind of a thing. So so you can have your own customized application for your community's needs, whatever is specific for your community, whatever is relevant for your community, you can have those implemented in your server. And but your clients still have a global reach and they can access people across the globe. So as you said, the video sharing example that we had. So right now what we can do, as you had said, that we can attach the video in the message and people can see that. So that happens even now. You can attach a YouTube videos link on a Facebook message and share it across and people will be able to see that. But what we are proposing is, if you want to interact with that video, if you want to comment on that video or like the video or do have some kind of an interaction, that you can't do now. So if you have a Facebook login, you can't comment on YouTube video. But with this, what we are thinking of is, even if I'm part of a different network, I can still interact with the content from a different network and people will still be able to see me. One more important factor is, as time proceeds, there are new technologies coming. Every year has some new social network introduced. So in 2010s, Facebook was the big thing. And then people were very much in Facebook. And then after a while in 2015-16, our time, it was Instagram when we were in college. And Instagram was the next big thing. And then now it's TikTok. And I myself don't know much about TikTok. So with this idea, what you can do is, even when new social networks are onboarded to the network, you don't have to have any user migration. You can have the same user which you created for the network that is already there in the system and use that profile to interact with this new platform, which has the new platform. Yeah. And as in YouTube, you have to have this model of subscription. So you subscribe to a particular channel, and then you interact with that content. So here there can be such relationship across platforms. So a subscriber for a YouTube video can actually be a user of Facebook. So those things are also possible. Now future work. So this is where it gets interesting. So the ledger, the client log that we actually showed. So that is, right now we are just implementing a simple queue in which servers post messages of the new client signups. What in future, what we can have is we can have a transaction distributed ledger. So every time there is a new sign up or something like that, it gets recorded in this ledger. Now, the problem with your traditional blockchain ledgers is that you have to calculate a hash every time you want to insert a new record, which is very time consuming, and it might not be practical in our case. We can't always have this intensive hash calculation. So other than that, if we integrate this with a cryptocurrency or a cryptocurrency based chain, what happens is the people who have higher value in that network. So when I say higher value, they might be holding a lot of that particular cryptocurrency. They'll basically, it becomes a proof of stake kind of a concept, and they'll basically authorize whether a particular entry in the ledger is valid or not. And for economic reasons, they won't lie. So that is one of the things that we are thinking of. The second thing that is the obvious problem of the latency that will be there in the network, because even right now there are so many places which do not have the same bandwidth, and then there's the general problem of communicating across servers. So that is one area of opportunity. And with Web 3.0, virtual lands and NFTs are becoming a big thing. So people are spending millions of dollars to buy virtual lands. So what with this particular protocol, what we'll have is you can build your own, like this virtual house. You can host it on your own server. You can let people from the world access it, buy it, and even organize events, meetups. So all this happens on your own server. You can spin it up, just implement the required protocols, and you are able to connect throughout to all of the people outside. And so this makes the user a owner rather than just a consumer. So yeah, that's it. Yeah, thank you.
Okay.
Yeah, some answers to that question.
That's great. Okay, so I'm going to say a few things. I might already forgot some of the things I thought about. Okay, number one, this is a simple thing, is that I have an implementation about a social network, which is a single. So it has a functionality like a mini Facebook. So it basically is a server and a client program talk in the JSON RPC that you can actually do a post. You can do a post, you can comment, you can share a link. It basically provides the information, a social network handle in the JSON level, so you can allow multiple clients to be able to share, to be able to comment. It's open source if you want to, but that's basically one server, and it has a capability to do search as well. This is basically search and the social interaction, and it's basically open source. So if you want to develop a more of a demo, because you have the authentication that connect to server, and then if you add this in, you can actually do a cross-platform sharing and things like that as a prototype, just let you know that. Okay, so that is just information for you to see if it's useful. But what I'm really interested in, what you're looking at is, I hope I still remember, this is the most important point I would like to emphasize, that, okay, so far your platform, either your idea or the Fediverse, your idea is actually allow, in your example, using one client on one platform to be able to interact with client in the other platform. And the protocol basically provide the interoperability. Okay, so let me actually propose something maybe similar, but maybe a little bit different. So, so the thing is that this two platforms, they might have a problem to actually want to do this, because why? Because when I open up, assuming on Facebook, I actually open up to let the other, say Twitter, to be able to let the Twitter's client to communicate with a Facebook client, then I don't have an incentive, right? I'm actually losing that opportunity for that particular Twitter client to actually move into my service.
Yeah.
Now they don't have to. They can just directly communicate.
Yeah.
Okay. So the alternative I'm thinking is it has to be fair in the sense that if the Twitter client want to talk to Facebook client, then we actually want to see this activity present in both platforms. So essentially, it looks like it's still the Twitter client is communicating with a Facebook client. But in Facebook's whatever the social informatics, they actually see a virtual Facebook user talk to the Facebook client in client 2. And in the Twitter, it actually look at is a client in Twitter talk to another virtual client in Twitter. So essentially, the interoperability not just provide a message passing as identity, they actually share the interaction in both platforms and such that both platforms will see some of the activity. So then Facebook will look at this a little bit different. They say, okay, wait a minute. When I allow this, I actually improve my content interaction because that Twitter user is actually going to bring in some interesting content. It's similar for like a YouTube, right? YouTube now, if I actually make a comment, it's only in Google. But if I share that link in Facebook, the YouTube link, and when people click like, then there is some social interaction on Facebook. If both platforms can actually share both interoperable, then essentially this becomes a benefit for both because now they can compete. I mean, in this case, actually, Facebook will feel a lot more comfortable because Facebook thinks he can compete. So they will actually be able to do that. So the concept is think about not just the communication, but how the content will be virtually be placing. I mean, the other example you have at the end, you actually look at the virtual LAN, right? You develop a virtual LAN, you invite people to come in with different platforms to do that. It will be really nice if the other person on the other platform also have a virtual LAN. And when you're doing this, it's actually happen party in both virtual LAN. It's the same party, but it's actually have a different setup. And this will be an interesting incentive for different platforms to be integrated. I think that is something which I think they might we should try. By the way, what you're doing is really important. I have seen people trying to propose. What we are actually propose is an internet among all the content, social content, and we provide internet at layer 7 or 8 or 9, which I think it should have happened, but it didn't happen. But I think your work might lead to a successful solution. That's actually eventually, I think that is actually more important in layer 3 internet, because if we can connect at the layer 8, layer 9, we're helping each other to make the social. I mean, your idea of integrating the blockchain or the cryptocurrency, I think it needs to happen. By the way, I'm not familiar with that, how that will work, but I feel in this kind of social content, because it's going to be decentralized, you have to have some way to provide a integrity or some kind of validity proof about the information. And therefore, Facebook, they don't need to worry about that. But across Facebook and YouTube, we better have something like that to actually, go ahead.
So that was, so if we this authenticity, how do we determine whether a particular sign up is authentic? That question is definitely important, because how do servers, two different servers, trust the other person's client? So that's where I mean we were thinking that maybe we can have this, like a consensus between people who hold large amount of the currency, whichever cryptocurrency is supported, right? So if they don't vote to the correct person, or if they are voting for a wrong entry, then what happens is the value of their currency will fall, and that will be financially negative for them. So they won't do that. So with this basic like economic structure, not a proper mathematical hash function, but just a economic incentive, we can have this proof of originality. That's what we were thinking of.
Okay, that's great. Yeah. Okay. So I have some questions I want to ask you, and maybe I should, maybe I should turn off the recording first, and then I will ask the question. Okay.
Yeah,
Okay.
sure.